can be done by using 2 pointers, which are initialized to point to the first elements of the arrays. And we compare the elements pointed to, copy the smaller one to the near array, and increment the index of the smaller element. And then we repeat this operation until one of the two given arrays is exhausted. Then the remaining elements are copied to the end of the new array. Okay? Now I will write the pseudocode for this. We already discussed it. And then we will go over the pseudocode. Algorithm merge. So we have I, j, and k pointers. While I is less than p and j is less than q, p is the total number of elements, and the last index of the array B is p, and the last index of array C is q. So we go as far as we can. If bi is less than or equal to cj, then we copy it. We take the minimum one, the smaller one, always. Whichever is the smallest, we get it, and then we increment the corresponding index, okay? K gets k plus 1. And then if I have reached the end, if one of them is exhausted, then I copy the remaining one. If I is equal to p, which means that array B is exhausted, so I copy the remaining ones in C, copy C from J to Q minus 1, to A, K, to P plus Q minus 1. Else, that means C is exhausted, so I copy the remaining ones in B. P plus Q minus 1, okay? So if we want to go on an example, so that's how it is divide and conquer. Let's say I have these 8, 2, 10, 4, and I want to sort this out. I divide only by the number of elements, okay? I don't, dividing operation is extremely simple. So I do this division as equal to 2, and then one of them is this 6, 5, 7, 1. The other array is 8, 2, 10, 4. Okay, so I sort them within each other recursively. So how do I do this recursively? I again divide them into 2, 10 and 4. Okay, so how do I do it now? It's like 6 and 5 now, 7 and 1. Again, the recursive division is here, 8 and 2, 10 and 4. So how is this? Now I do the merging operation of 6 and 5 with 2 pointers. It becomes 5, 6, and this becomes 1, 7 with 2 pointers, and this becomes 2, 8, and this becomes 4 and 10. Okay. Now I keep on with the merging, going back up the recursion now. So to merge 1, 5, 6, and 1, 7, I have like 2 pointers like here. I take the minimum one, And then this goes to 7, and I take the minimum one, which is 5. I advance it 6, 7. Okay. And with these ones also, I have like 2 pointers. 2 is the minimum one. I advance it. Now 4 is the minimum one. I advanced it. 8 and 10. Okay. So now how do I merge these two? Again, I have like 2 pointers, 1 and 2. 1 is the minimum one, the smaller one. I advance it. Now 2 is the smaller one. I advance it. It's 4, 4 and 5. Now 5 is the smaller one. I advance it. 6 and 8. 6 is the smaller one. 7 is the smaller one. I am exhausted with this part. Now I copy the remaining here, 8 and 10 to here. And I'm done. Okay. So that's the example. So how do I compute the complexity? Now this complexity n, first of all, I divided it into 2, right? So I had 2 arrays with size n over 2 each. So the recursive formula is 2 times c n over 2. Plus, I had this, I divided it into 2. I did sorted them recursively. And then I did what? I merged the 2 arrays. I merged these 2 subarrays, which has complexity C merge and which is linear. Okay, the merging operation. At each step, exactly one comparison is made. Is needed. In the worst case, neither of the 2 arrays because once one of them becomes empty, I'm like already done. I just copy the remaining ones to there, which takes constant time, okay? Which doesn't take much time. I don't do any more comparisons. Once I run out of one of the subarrays, the rest is straightforward. I don't do any additional, any costly operations, comparisons. So in the worst case, neither of the 2 arrays become exhausted, okay? In the worst case, neither of the 2 arrays become empty. Before the other one. Bu arada koridorlarda falan dikkat etmenizi tavsiye ederim. Fakülte hocalar arasında da Covid falan var. Bilginiz olsun, tamam? Ya Covid ya temas sayısı oldukça yüksek şu anda. Of the 2 arrays become empty before the other one. Contains just one element. Okay? So we will write it in the worst case. It's the same anyway. Is n minus 1. And we have C worst n is equal to 2 times C worst n over 2 plus n minus 1. So I can apply Master's theorem and I can actually find this. C worst n is equal to n times log base 2n minus n plus 1, something like that. So it's, let's say, big O n log n. It's also theta, but anyway. So what if n is odd? So in this example here, I picked an array with 8 elements, which is a power of 2. So that's why in all the divisions, I always end up with even, except in the last one, 2 elements, which becomes 1 and becomes straightforward, okay? But this doesn't have to be the case. In any of the recursive steps, or even at the beginning, n can be odd. But that doesn't change things much. In this case, it will not be exactly evenly distributed. There's going to be one difference. So then I can write it as this. One of them will be the ceiling of n over 2, one subarray. The other will be floor of n over 2 plus Cn, which is n minus 1, okay? So asymptotic bounds do not change. For instance, if I divide a list into 3, and this is called multi-way merge sort. I divided it into 2 and then operated it, but I could have divided it into 3 or even 4 maybe, okay? Then how would I merge? I would apply the same principle, the same mechanism, let's say. Now I will have 3 subarrays and I will have 3 pointers. Again, in the beginning, all of the 3 pointers point to the first elements of these subarrays. And then I take the minimum one, I copy it into the new one and advance it. The other ones stay where they are, okay? And then I do this, whichever is the minimum, I copy it, I advance its pointer and go on like this. And at the very end, let's say one of them is exhausted, then I'm left with, let's say, 2 subarrays. If I'm left with one of them, I can just copy it immediately, okay, as I did in the beginning. But if I have like 2 of them, then I can continue the same operation of merging with 2 ones, okay? I can continue the same operation with the remaining 2 pointers and take the minimum one, etc. Okay? So 3-way merge sort, I can do this. Divide the list and then merge them together. So with 3-way, let's say 3-way merge sort, the complexity is, for some reason, I don't know, it's because of the internet, I think it's too slow, okay? 3 times Tn over 3 plus n minus 1. Now I can use the master's theorem. A is equal to 3, B is equal to 3. Fn is theta n. So that means D is 1, okay? So A is equal to 3, and that is 3 to the power of 1. So I can say, again, with master's theorem, that Tn is in this theta and log n class, okay? So I think this is obvious if we understand the 2-way merge sort, which is the default one, then the mechanism is more or less the same. So if we compare merge sort, what can be its advantage? Over quicksort, maybe. And also heap sort, which we didn't see in this class, but I think you know it from data structures. Even if you don't, you can Google it. Is what? Do you remember what we said in the very beginning of this course? The properties of sorting algorithms, in-place sorting algorithms, or we talked something about stability. Remember? We said insertion sort is stable, but we said quick sort is not stable. We said insertion sort is an online algorithm because it doesn't need any additional space. sorry, online algorithm, because I can apply it in an online manner on the fly as the numbers come in. Okay, it can be done simultaneously. But stability was, remember, we had like, we gave an example called like, I have like, let's say I have 3 entries, Ali Güngör, Veli Güngör, and something like that. If it's a stable algorithm, then it's and if they have the same value, then their places in the sorted version will be according to their initial positions. I mean, if one comes before the other in the initial position in the input and they have the same value, then in the sorted list, again, the first one will appear before the other ones in the memory. That's might be an advantage, we said, on, for example, you want to sort it out according to the names. You have a database of people's names and last names, and you sorted them out with last names first, okay? And then you sort them out with the names again, okay? In this one, if it's a stable sorting algorithm for people with the same name, okay, they will appear consecutively, of course, in the sorted list. But because you applied the sorting before, and because according to the last names, you applied it before, and because the algorithm you use is a stable sorting algorithm, then among the people with the same names, within each other, they will be sorted according to their last names, which is a property that might be deserved very frequently, okay? And quicksort does not have this property. But merge sort has it, okay? Is its stability. But of course, at the expense of what? What is the disadvantage? Just to remember your data structures knowledge, maybe. Yes, additional memory. The principal shortcoming of merge sort. I mean, insertion sort had all these properties and it doesn't use any additional memory. It had the stability and online property, but its complexity was n square. Here, we have the same complexity as quicksort, and we have an advantage called it be stable in contrast to quicksort. It's stable, but we have additional memory, okay? There is like a principle that applies in engineering, I think. What was it? Price, place, something. 3 things. I don't remember the exact one. Choose 2. That you cannot have 3 things at the same time. If it's, it might be more expensive or fast, cheap, reliable. Choose 2. Okay, this is like a basic engineering principle. I mean, you can't have fast, cheap, and reliable all at the same time. For instance, insertion sort is costly, so in terms of complexity, things like that. So you have to choose between the 2, and this is, I think, something that applies for insertion sort, quicksort, and merge sort also. There are like 3 properties we desire, and each one of them has 2 of these, sort of. Okay, you cannot have all. The principal shortcoming of merge sort is the linear amount of extra storage. I mean, there is always an extra storage required to keep track of the variables, things like that. But as long as this extra storage is in a constant amount, then it's fine. You can just store some variables, use a few registers, that's okay, okay? But here, the amount of memory you require is linear with the amount of the input. So it's that's the problem. It's not only that it requires extra memory. I mean, all problems, all algorithms require a little amount of extra memory, but here it's linear extra storage, the linear amount of extra storage the algorithm requires. Although merging can be done in place, the resulting algorithm is quite complicated. There's a version of this where this merging can be done in place without an extra memory in the literature, but the algorithm is way too complicated, okay? So let me write this also. Old engineering principle. Fast, cheap, reliable. Choose to. You cannot have all. That's the thing. Okay, so are there any questions about merge sort? No? If not, then I will continue with quick sort from the divide and conquer perspective, okay? It will take a little bit of time, okay? And we will count inversions. So unlike merge sort, böyle kaldı. Quick sort divides them according to their values. So it's the division step that is important. Okay? Partition. So what do we mean by a partition? So that's AS is called the pivot, okay? So I want to partition it so that they don't have to be sorted within themselves. They will be eventually, but not in the beginning and not necessarily in the intermediate steps. So this is all are less than or equal to AS. And then we have AS, and then A is plus 1 and A n minus 1. All are greater than or equal to AS, okay? So this is what we want. So in merge sort, the division is obvious and the entire work happens in combining their solutions. Okay. The entire work happens in the division stage with no work required to combine the solutions to the subproblems. Okay, so that's the difference. So let's write the pseudocode for quicksort and then talk about another partitioning algorithm. So if L is less than R, so it's the left corresponds to the left and right, which is all, of course, the case. If unless we have only a single element, which is obvious. So we first partition it, and we will see how this will be done. Partition the entire array according to this S is a split position. Quick sort, and then we sorted the left part according to quick sort, which is this left part, and then we quick sort S plus 1 to R. And then we return this left pivot and right parts. Okay, so here for the partitioning, let me write this here. A partition algorithm is a partition algorithm. We can certainly use Lomuto partition, which we have already seen, or another one. Or a more sophisticated method by Hoare as follows. So that's what we will see here. Another partitioning algorithm I will talk about, okay? So we start by selecting a pivot, okay? We start by selecting a pivot, an element with respect to whose value we are going to divide the subarray. So we will make the division according to the value of this element, the ones that are smaller than this element's value and the ones that are greater than that. And this element is called the pivot element. So how do we choose it is a subject of another research. There were many studies done in that direction. And now we will just do the simplest one. It could be random. I mean, it was shown that taking the median one is simpler, but how do we find the median element is another level of complexity that we need. Or we could have chosen it randomly. Okay. For now, do the simplest selection. Choose it as the first one. As far as our complexity analysis is concerned, it doesn't matter, okay? Choose the selection mechanism does not change the asymptotic complexity, okay? But it may make some changes in practice, okay? So not asymptotically. Now, we will see another algorithm called horse partitioning algorithm. I will start it a little bit because we started a little bit late. I will leave at 2:30 for a break, and then we will continue. So unlike the Lomuto algorithm, sorry. Now, scan the subarray from both ends. So now I scan it from both ends, okay? From here and here. I scan it from both ends. So I is the index. Denotes the left to right scan and starts with the second element. So this is I and this is J. Starts with the second element. This scan stops upon encountering the first element greater than or equal to pivot. Okay. So I encounter something that is greater than or equal to pivot. I stop. Okay. J denotes the right to left scan. And starts. Here I start with the second element because remember I said that I select the first element as pivot. That's why I start with the second element in the left to right scan, which is done by the pointer I. Okay. J denotes the right to left scan and starts with the last element. Okay. This scan stops upon encountering the first element that is less than or equal to the pivot. Okay? This is when we stop. So once both pointers stop, then I need to take some action, exchanging them and then going forward in their original directions, etc. Okay? So let me describe this graphically more. So the first one is the pivot element. I start my scan. The structure is like this. Here, there are some elements that are less than or equal to P. So I proceed in that direction, but the I pointer stops when it sees an element that is greater than or equal to the pivot element P. Okay? And then there are some other things in between. I don't know about them yet, but the other pointer, J, comes from the right. Okay? This is J, and it stops once it sees an element that is less than or equal to pivot. Okay? And because it comes from here, right to left, it proceeds as long as there are elements that are greater than or equal to the pivot element. Okay? When we stop, they are in this position. Okay? The structure is like this. So after both scans stop, three situations may arise. And we will analyze these three situations after the break, okay? Your look started to change, so I was originally planning to take a break 5 minutes later, but we will take now, okay? Because this is a little bit complicated, I need more concentration from you, okay? For the remaining. I'm not closing it as usual. We'll see online class, we'll meet 10 minutes later. Bye. Tamam sanırım. So, after both scans stop, three situations may occur. So the first one is almost exactly like what we have described here. They haven't crossed. Crossed means I comes from here, J comes from here, or maybe from UC, I should throw the rest. This is I, this is J. And they haven't like gone like this, okay? I is still less than J, it means, okay? The first one. If I and J have not crossed, I is less than J, we simply exchange AI and AJ and resume the scans by incrementing I and decrementing J. Okay, so they go on in their usual directions. Okay, we simply swap them. Once we swap them, this becomes what? This becomes something that is less than or equal to P. Oops. Ne yaptım? Less than or equal. Aha. Şey yaptım yok, ne oluyor? Bir dakika. This becomes something that is less than or equal to P. And this becomes something that is greater than or equal to P. So it's like this window has been extended and this window has been extended, and they go on in these directions, okay? So what happens if they have crossed over? If I and J have crossed over, it means I is greater than J. So it's somewhere like this. I was coming in this direction and J here. And so this is I and this is J. Okay, they have crossed over. So when did this happen? So it becomes something like this. So I will continue it here, but I will first describe it here. I have P here, and all are less than or equal to P. And then I have something that is less than or equal to P. And I was going on in this direction, J, and I was in this direction, J. If they have crossed over, and before that, the remaining parts were like this, all are at least P. So this is greater than or equal to P, and this is all are greater than or equal to P. Okay, so this is if they have crossed over, the situation is exactly like this, it means. Okay, that's the case where they cross over. Because I comes from left to right, and when does it stop? It stops when it sees an element that is greater than or equal to the pivot. Here, I saw an element that was greater than or equal to the pivot. Look at where I have, okay? And J stops when it sees an element that is less than or equal to the pivot. That means everything is already partitioned, right? It means the partitioning ends here. That's why they crossed over and stopped. Okay, they cannot go on any further. It means we will have partitioned the subarray after I can exchange it with the pivots now. Okay, after exchange, because it's already done. after exchanging the pivot with AJ. I exchange the pivots now with AJ. So this becomes something less than or equal to P, and this becomes something exactly P, and the rest is already greater than or equal to P. Now it is partitioned into two, okay? With the pivot AJ. Is this clear? It means I'm already at the end of the partitioning algorithm. I cannot go on any further. Everything is done, and the situation arises such that they crossed, okay? They crossed means that they can cross only one element to the others. So they cannot go on any further. If they were able to go on any further, they wouldn't cross. They have already finished their ways, their paths, okay? So the third situation is if they don't cross, but they still stop. This means when one comes from left to right, and the other comes from right to left, and they stop, and they didn't cross. It means that both point to the same element, right? That's the only way it occurs. They didn't cross. If they didn't point to the same element, and they didn't, then they would have crossed when they reached the end of their operation, okay? If I and J stop while pointing to the same element, in other words, I is equal to J, the value they are pointing to must be equal to P, the pivot, right? Because it proceeds as long as the elements are less than or equal to P and the other greater than or equal to P. Both less than or equal to P and greater than or equal to P implies that it is exactly equal to P, okay? And that's the element that both of them are pointing to. If both of them are pointing to that element, it means both of these conditions are satisfied, which means that the element that they are pointing to has value exactly equal to P. If I and J stop while pointing to the same element, the value they are pointing to must be equal to P. Thus, we already have the subarray partitioned with the split position S I J, okay? So it's something like this. I have P, I have all are less than or equal to P, something that they are exactly equal to P. J is equal to I here, and all are greater than or equal to P, okay? So I don't need to do anything any further in this, it's already done. I'm already at the end of the algorithm. So let's write the pseudocode for this algorithm, which is called Hoare partition. This is the pivot. Repeat until I is greater than or equal to j. If I is strictly greater than j, then we're in case 2 that we described, that they have crossed over. And if they are equal, then we are in case 3, which it means that they're pointing to the same element. Okay? So we operate until either case 2 or case 3 holds. Okay? So we operate as long as case 1 is true. Okay? So once we do that, then we swap AI and AJ. Undo last swap when I is greater than or equal to j. Swap AL and AJ and return J. Okay, so that's the end of the pseudocode of the operation. So once this is done, I swap AI and AJ and then AL and AJ. So I arrange their positions according to the pivot. I just simply put pivot in its correct position. Okay, at the very end. So what's the efficiency? Again, you can intuitively see that it's linear. So the number of key comparisons made before a partition is achieved equal to n plus 1 if the scaling indices crossover and n if they coincide. Because if they have crossed over, like here, 1 points to this, and then look at the number of elements that they have scanned. Okay, if they didn't cross over, like here, they stopped while pointing to the same element, both of them, then they have made, if they coincide, they have scanned all the array and they didn't do any additional comparison. They have accessed n positions, and that's why the number of key comparisons that they made is n. If they have crossed over, like in here, it means one of them, they made one more access. So it's n plus 1. It doesn't change things, but there's just a plus 1 difference. If all splits happen in the middle of the corresponding subarrays, we have the best case. Okay. According to the master theorem, so this is obviously theta and log n. You can plug in the values, the corresponding values, and you can see that it's theta and log n. Solving exactly for n is equal to 2 to the power k yields that so in the worst case, I don't know if you can see it. Maybe this is better. Zoom'la ilgili mi bir şey var? Benim gördüğüm gibi görmüyorsunuz. Tam sağ tarafları tam görmüyorsunuz. Şimdi görüyorsunuz. Tamam. Yani ama ben evet şurası gitti bu sefer de. Worst case. In the worst case, after all the divisions, they are skewed. Okay, only one element remains. In the worst case, all splits are skewed to the extreme. Burada gayet şey görünüyor. Projektörden olduğunu düşünüyorum ben. Projektörün zoom'unu azaltabiliyor muyuz acaba? Şeyi mi kaymış? Kumandalık bir şey mi? Çok emin değilim ama. Böyle olur mu acaba? Zoom eksi diye bir şey gördüm ama bir şey değişmiyor değil mi? Şimdi böyle yap. Daha mı iyi? Biraz daha iyi galiba. Yaygınlaştırdı evet. Aspektini değiştirdik ama eskiye de alamıyor şimdi. Being partition. Ben bilgisayarda gayet şey görüyorum çünkü. Burada gördüğüm gibi görüyorum. Hiçbir sıkıntı yok online'da. Projektörde şey var. Neyse. Bir sorun yok herhalde çok da. So this situation occurs for inputs that are already sorted. And of course, I take the pivot element as the first one in that case. That's why it occurs there, okay? So this is like A0, and this is A1, AN minus 1, So n+1 comparisons are in iteration 1. And comparisons in iteration number 2. And then in the very end, 3 comparisons in the last iteration. Okay? So I have like, if I sum them up from 1 to n+1, it would be n+1, n+2 over 2. But because I don't have 2 and 1 here, which makes -3, doesn't change the result, but still I need to make this. So this is theta n square. In the worst case, it's n square. We did this before. Now we will make the average case analysis again here. With divide and conquer. On the average, a partition can happen in any one of the cases, okay? A partition can happen in any position S görün diye şöyle yaptım. Tam görünüyor çünkü. To achieve the partition. Okay, we have made the partition. Once we achieve it, the left part will have S elements because it's it's made with the position S, and the other n-1 minus S elements, okay? So as indices start from 0, indices from 0 to S-1, it's the left partition, and then I have the value S, and then the remaining ones, okay? So that's why it's like comes from 0 to until S-1. This is the left part. S is the pivot, and then I have the remaining, which is n minus S minus 1, okay? N minus S minus 1 elements. And here I have S elements, okay? Assuming that the partition split can happen in each position S with the same probability we get the following recurrences. So on the average, 1 over n times summation s from 0 to n minus 1 s from 0 to n minus 1. So I have n plus 1. N plus 1 is for the partitioning operation, okay, plus C average S. So for the recursive step, for the left partition takes CS time, and then the average n minus S minus 1, the recursive step for the right part, okay, for n greater than 1. So C average 0 is 0, of course. And if I have just 1, then I don't need to make any comparison. It's also 0. Its solution, we already made this, remember, from 0 to n minus 1, n minus 1, 0 in the previous parts. So I won't do it again. C average n is like n log n. Okay. So there might be better pivot selection methods. Better resulting in practice. So switching to insertion sort. On very small subarrays is one option. Like 5 to 15 elements, I can use insertion sort there because it doesn't matter much, and it might even be better a little bit, okay? There might be modifications of the partition algorithm, such as three-way partition, etc. And quicksort is not a stable algorithm, okay? So we don't have this stability property. Quicksort is not stable, okay? So any questions about quicksort and its analysis? Because I will move to another problem that you don't know from before this time. I will start it and then we will continue it tomorrow. Do you have any questions about quicksort? So we did merge sort and quicksort today. We will also talk about counting the number of inversions here. Okay? That's what we will continue with. What is an inversion? Do you remember? We are given an array of integers. An inversion is if there is some element, I mean, I have sorted them with some property. Let's make it numbers. 8, 2, 5, 4, 1, 9, 6. Okay. So when I sort this, it becomes a sorted array. A sorted array does not have any inversions, zero number of inversions. Inversions is if there are two elements that are out of order, then this is an inversion. One is bigger than the others, but it becomes before that, like 4 and 1 is an inversion here, okay? But it doesn't have to be subsequent, consecutive elements. It doesn't have to be that, okay? So, for example, 8 and 5 is also an inversion because 8 is bigger than 5, but it comes before that, okay? There are other elements in between, so 8 and 2 is also an inversion, but 8 and 5 is also an inversion. 8 and 4 is also an inversion. But 8 and 9, for example, is not an inversion. Okay? So they form an inversion with 1 always, because 1 is the smallest one. So it forms an inversion with all the elements that are coming before that, right? For example. If it's sorted, once I sort it, for example, in this example, once it becomes 1, 2, 4, 5, 6, 8, 9, I think, then I don't have any inversions. So whichever two elements I select, if one comes before the other, then its value is smaller than the other, okay? So the question is, so the least number of inversions, the minimum number of inversions is when it's sorted. So 0 inversions means it's sorted. What is the maximum number of inversions? Or first, maybe you may want to think the case, when does the maximum number of inversions occur? If it's too far from being sorted. Sorry? Yes, if it's reversely sorted, then I have the maximum number of inversions, right? For example, here, if it's 9, 8, 6, 5, 4, 2, 1, for example, then it's reverse sorted. If it's reverse sorted, then what is the number of inversions in that case? Think about it as an inversion is defined on what? We say that there is an inversion between two integers, right? Two distinct ones. If one comes before the other and its value is larger. So in reversely sorted, if I pick any two elements from this set, 9, 8, 5, pick any one of them. Is it an inversion? If it's reversely sorted. 9, 8, 6, 5, 4, 2, 1. I pick any one of them. Just tell me two of them, for example. Online class, are you there?
Yes, ma'am.
So answer. I'm expecting an answer from the online class now. The actual class is already dead. I don't have any hopes.
What was the question? If we choose any of them, is it inversion? Yes, it is.
Okay, the question, tell me one guy from the class, from the actual class is going to tell what the question is. What's the question? Sorry? Tell any two numbers from this list. This list, which is reverse sorted. Give me two numbers from this list.
6, 5.
Okay. Give me two numbers that are not consecutive. Because I said that they don't have to be consecutive.
9, 4.
9, 4, okay. 6, 5, is it an inversion or not?
It is inversely sorted.
It's reversely sorted, I know that, but I'm asking you, is 6 and 5, do they constitute an inversion or not?
They are.
They are? I can't hear you.
They are.
Repeat.
They are. They are
They
counted.
are, yes, they are inversion. What about 9 and 4? Are they in inversion?
Yes, but they are not consecutive.
They are not consecutive, but it's not important as far as the definition of an inversion is concerned. If one comes before the other, it means they don't have to be consecutive. There might be other numbers in between, but still it comes before the other one. And its value is greater than the other one, which is something that they don't have to be. Okay, in order for it to be sorted. In order for it to be sorted, I don't want any inversions at all. And just observe that in this partitioning operation, when I swap them, the I and J pointers, what am I actually doing when I swap them? In this partitioning here. I swap them, right? Here, I swap them. But I points and J points. What am I actually doing? I'm getting rid of an inversion, right? Because they are out of order. I swap them and I fix it. But of course, when I'm doing this, maybe I fixed more than one inversion. I don't know what comes in between. Because when I fixed it, maybe the others also got fixed somehow. Okay? For example, if 9 was in the beginning, let me show it from here. When I, for example, swapped 9 and 4, so this becomes 4 and this becomes 9, I also fixed the inversions of 9 and 6, 9 and 5, etc. Okay, now 9 comes after them, for example. I fix at least one inversions and possibly many inversions. Many, possibly, but at least one inversion. So when I swap, with the swap operation, I'm getting rid of an inversion. So if it's reversely sorted, if I pick any two numbers, any one of them, consecutive or not, do they constitute an inversion or not?
They will be counted as inversion.
Yes, they will be an inversion. When it's reversely sorted, I said that I have the highest, the maximum amount of inversions. And when I pick any two numbers, they will be an inversion. Okay? So what's the total number of possible inversions then? I pick any two numbers from n numbers, and they are in inversion. How many pairs can I pick? I know that for sure they will be an inversion if it's reversely sorted.
Pair combinations of 9.
Yeah, not 9. 9 was just an example. Forget. I could have picked 6 and 2, 6 and 1. It could be anything. What's the total number of inversions here? Any pair constitutes an inversion, right? So if any pair is an inversion, and if I want to count the total number of inversions, then I need to count the total number of pairs, right? I have n elements. How many pairs do I have? Ordering is not important. When I count, it's not important. But of course, in order for them to be an inversion, ordering is important. But I know for sure that because it's reversely sorted, it is already an inversion. What's the number of pairs in an n-element array? What is a pair?
n times n minus 1 divide 2.
N times n minus 1?
And division 2.
Yeah. Division 2. Because it's n choose 2, right?
Yes.
And n minus 1 over 2. Maximum number of inversions which happens when it is reversely sorted. So why do I need this information? How many inversions do I have? Why? Now I will find, we will, maybe tomorrow, see an algorithm, a divide and conquer algorithm, which counts the number of inversions. What would be an exhaustive search approach for this to count the number of inversions? I can check each pair and see whether they constitute an inversion or not. I don't know if it's reversely sorted or if it's sorted. It could be anything. I'm talking about the general case here. I can just enumerate all possible pairs and see if they are in inversion in the list or not, okay? And because there are n choose 2 number of possible pairs, I need to check n minus 1 over 2 number of pairs. So an exhaustive search approach to count the number of inversions would be n minus 1 over 2, okay? It could turn out that there are 0 inversions or there are n minus 1 over 2 inversions. Counting the number of inversions, we will see an n log n algorithm, not an exhaustive search algorithm, because an exhaustive search algorithm would give us n squared time complexity, and we will see a divide and conquer algorithm to count the number of inversions. But why would I be interested in the number of inversions? Remember that insertion sort had operated well if it's close to being sorted. Remember? But for quick sort, it's the reverse. If it's sorted, then it's not good enough. I mean, the more far away from being sorted, the better it is, kind of, okay? So if I have some kind of a metric, I don't know the list, but I don't know the sorted version. If I had done that, I would have finished the sorting anyway. But gives me some measure of how far away from being sorted it is. If it turns out that the number of inversions is not very large, it's somewhere close to 0. I mean, how far depends on how I define being close to 0 is, but I know that the minimum is 0 and the maximum is n minus 1 over 2. If it's somewhere in that region, it means that, and if I already have an n log n algorithm for that, counting the number of inversions, which is divide and conquer, and we will see tomorrow, then I can say that without sorting them, if I sorted, I would have already done do the work, but I'm just trying to decide which one would be better. If it's close to being sorted, then I can say that, okay, maybe I don't need quick sort here. It's close to being sorted. I counted the number of inversions with n log n time. Now I can apply insertion sort. It would be better maybe than quick sort, okay? Because it's close to being sorted. So this gives me a matrix, a baseline, so that I can decide whether to use insertion sort or quick sort, okay? And if I can do this counting better than n squared time, and we will see how, we will see a divide and conquer algorithm for that, then I wouldn't even, I mean, if I did this counting already in exhaustive search in n squared time, then if in the results I decided to use quick sort, which is n log n time, then it wouldn't make sense, right? Even the counting would be n squared and it would dominate the quick sort. So why did I do this? So it's good if I make it n log n time, so I know that I will not exceed the computational complexity of quick sort, so that if in the end I decide on using quick sort, then it will be better than not doing this counting and etc. Okay, so that's why it's useful to count the number of inversions. See you tomorrow, guys. Bye.